Hey everybody, welcome to another lecture video. We're going to continue learning about Earth systems and resources, and today we're going to talk about something that's in the air. And we're going to be able to answer a couple interesting questions such as why and how are there tropical rainforests right next to deserts? Why is England so much warmer than Canada despite being on the same latitude? And why was Ben Franklin such a cool dude? All this and more when we learn today about the atmosphere. Doesn't that taste delicious? That's right, the atmosphere. The atmosphere does a lot of things. It provides oxygen for us to breathe, CO2 for plants to breathe. It absorbs heat and regulates the climate by both moisture and temperature, and it helps the nutrient cycles, such as water, carbon, and nitrogen, cycle and transport matter throughout the world. Okay. The atmosphere is mostly made of nitrogen, 78%, with close to 21% being oxygen, and a wide variety of trace gases as well, depending on a number of different factors such as location and time of day. And this includes water, CO2, methane or CH4, and ozone or O3. The Earth's atmosphere has a very unique structure. I'll give you a hint. Can you guess? Yeah, it's got layers like ogres. If you don't know what I'm talking about, educate yourself. So the layers of the atmosphere are organized or arranged by temperature. Changes in temperature indicate sort of the different layers of the atmosphere, okay? As we go up in altitude, the temperature will change, and those changes will tell us what layer we're in, okay? So let's start looking at this graph and orient ourselves. The x-axis is temperature. 0 degrees Celsius here is freezing. 60 degrees Celsius is quite hot. Negative 100 is very, very cold. On this side of the y-axis, we've got altitude in kilometers, and on the right side of the y-axis, we've got pressure in millibars, okay? In the troposphere, this is the bottom layer of the atmosphere. It's also the thinnest layer of the atmosphere, topping in at about 10 or 11 kilometers, which is about 6 miles. This is where we are. This is where clouds and weather and climate change occurs. This is where air pollution builds up, such as ozone. We don't want that here because that's where we are, and that's what we breathe. As we go up in altitude in the troposphere, the temperature decreases. It gets colder as you climb a mountain, and the air pressure decreases as well. It's harder to breathe as you climb a mountain, okay? But once we cross into the stratosphere, the next layer, we'll notice that the temperature actually starts to increase as we go up in altitude. This is because of the ozone layer, which is in the stratosphere. The ozone layer is really good at trapping heat and protecting us from UV rays. That's a good thing. Ozone is dangerous to breathe, though, so we don't want it in the troposphere, just in the stratosphere. So as we go up in the stratosphere, temperature increases, and as we enter the next layer, the mesosphere, the temperature will decrease as we go up, much like it does in the troposphere. The mesosphere is where meteors will burn up, and it is one of the thicker layers of the atmosphere, but as we leave the mesosphere and enter the thermosphere, this relationship with altitude and temperature will once again reverse. As we go up in altitude, the temperature will increase. The thermosphere is where the northern lights are, and above the thermosphere is one more layer not depicted here called the exosphere. That's basically just space. Okay? A couple things to note here. First of all, as you go up in altitude, the pressure decreases, right? That's important to know. Additionally, as we go up in altitude, the temperature gradients will change, right? From increasing to decreasing. This is how we delineate the different layers of the atmosphere. The points in which we switch from one layer to the other are called pauses, and these indicate the transition zones between these temperature changes. So the tropopause is as we cross over the tropopause as we enter the stratosphere, over the stratopause as we enter the mesosphere, etc. Mesopause, thermopause above that. So let's talk a little bit about these temperature patterns, right? As we go up in the troposphere, we see a decrease in temperature. Why is that? It's because the air gets thinner, okay? Think about penguins. When they huddle together, they're really good at trapping their heat, but when they're all standing all alone, they lose their heat very quickly. It's the same with air molecules. The closer they are together, the better they hold heat. And at low altitudes, like down here at the troposphere, gravity is very strong, so the pressure is very high. It's very good at holding heat. But as you go up, the pressure decreases and the air becomes thinner, so it's not as good at holding heat, which is why it gets colder as you go up. In the stratosphere, however, the ozone layer traps heat, so as we go up in the stratosphere, it gets warmer. As we cross into the mesosphere, that air gets colder as we go up, again, much because it's getting thinner, much like in the tropopause. And then lastly, in the thermosphere, it gets warm as we increase altitude, and that's because we're getting closer and closer to the sun, and there's less stuff in between us and the sun, and so you're getting exposed to higher levels of UV and X-ray radiation, which will increase the temperature. Okay. But I have some breaking news for you. The atmosphere does not stay still. I just figured this out the other day, and I wanted to share it with you. I've decided to call it something called Wind Day. Okay, that's what I decided to call it. Wind, of course, wind. The atmosphere moves. You can see wind patterns change all across the globe. There's lots of sort of different wind currents that you may be familiar with, maybe the Gulf or the westerly winds, the jet stream coming across the U.S. And wind is driven by three main factors that we're going to discuss today: convection, the uneven heating of Earth's surface, and the Coriolis effect. Okay? Convection is the first one. This is pretty important. It's the idea that hot fluids, and I say fluids because it could be a liquid or a gas, hot fluids will rise because they are less dense. The molecules are more spread apart, and they rise. And cool fluids will sink because they are more dense. The molecules are closer together, so they will sink. We see convection in lots of things in nature and society. Hot air balloons use less dense air because it's hot to rise into the air. Your tea kettles and ovens will use convection to distribute heat amongst the cavity. And the mantle of the Earth's core, the magma that's in there, experiences convection, and that's what causes tectonic plates to move one way or another. The second phenomenon is the uneven heating of Earth's surface. Okay? Areas at the equator will receive more direct, more concentrated sunlight than areas at the poles because it's concentrated in a smaller amount of area, so that sunlight is more intense. It's at a more direct angle, whereas at the poles, it's coming in at an indirect angle, so that sunlight gets spread out over a larger area and is thus less intense. Another diagram here showing the same thing. Equal amounts of sunlight that are unevenly distributed due to the angle that they're hitting the Earth, because Earth is round, it's a sphere, right? So keep that in mind. Most of the direct sunlight is hitting the equator, or the most intense sunlight is hitting the equator. And the last thing is the Coriolis effect. This is a physics phenomenon. I won't get into too much detail, but the idea is because Earth spins, anything traveling across its surface, whether it's a cannonball or wind, is actually going to get deflected because certain parts of the Earth are spinning faster than others. The equator spins faster than the poles because it's traveling the same amount of distance or a larger amount of distance in the same amount of time. Okay, angular momentum is conserved for all your AP physics freaks out there. Okay, but the simple description that you need to know is that when things travel in the northern hemisphere, they get bent to the right. And when things travel in the southern hemisphere, they're getting bent to the left. And think about it from the arrow's perspective. If you're standing at this arrow and traveling in the southern hemisphere, you're getting bent to the left. Okay. The Coriolis effect, or the Coriolis force, affects wind. That's why wind can get deflected and blow east or west on Earth's surface. It's because the spinning of the Earth is deflecting the wind. And that even includes things like hurricanes. You can see the maps of routes of different hurricanes over the years, and you can see that they are bending across Earth's surface because of the Coriolis effect. And if we look at wind currents, generally speaking, we see that, hey, the ones in the southern hemisphere traveling north are getting bent to the left, right? Or left, correct. The ones in the northern hemisphere traveling to the south are getting bent, are getting bent to the right. Okay, so we can see the air is getting deflected due to the Coriolis force. So, convection, uneven heating of Earth, and Coriolis effect are what generate wind patterns. One wind pattern that you must be familiar with is called a Hadley cell. A Hadley cell is an air cycle that happens around the equator. You can see there's one in the northern part, northern hemisphere and southern hemisphere, from 0 degrees, or the equator, to 30 degrees north, and 0 degrees to 30 degrees south. These are two Hadley cells here. There is also Ferrel cells and polar cells, but we won't talk about those nearly as much. Okay. How does a Hadley cell work? I know you're dying to know. You're just screaming at your screen right now. Mr. P, tell us, please. I'm going to tell you right now. Take a deep breath. Okay. So we talked about how the equator gets the most direct sunlight, okay? It's got the most direct solar radiation. So that's going to heat the air at the equator the most, okay? Keep that in mind. Let's orient ourselves to this diagram here on the right. We're looking at Earth from the side. We've got 0 degrees, or the equator, here. 30 degrees north and 30 degrees south over here. So most direct sunlight is hitting the equator. That's going to cause air to heat up and rise because it is less dense due to convection. It's also going to heat up the water and cause increased rates of evaporation. So not only is the air warm, it's also very wet and very moist, okay? It just so happens because all of this evaporation is happening at the equator, as seawater evaporates, the water leaves and the salt stays behind. So the top of the ocean at the equator is actually a little bit saltier than other places, which is kind of interesting. So as this air rises up through the troposphere, we just learned that the troposphere gets colder as you go up. So as this air rises, it's actually going to start cooling off and losing all that heat, radiating the heat out into space. As wet air cools, it condenses into a cloud, and eventually all of that water moisture will precipitate down to Earth right over the equator. Okay, so we have high precipitation and warm temperatures here at the equator, and this air that has been raised up is now moving, getting pushed north to the 30 degrees or south to 30 degrees, and at this point it has lost all its moisture and is starting to cool off. Okay, so we've got cool, dry air getting pushed away from the equator, and cool air is more dense, so it's going to sink. So that air will sink at 30 degrees north and 30 degrees south. And remember, it's dry. It lost all of its moisture at the equator when it rained. So this dry, cool air is sinking at 30 north and 30 south, and as it sinks, it will start to pick up warmth radiating from the Earth's surface. Okay, and it hits 30 degrees in north and south, and then it will start getting sucked in back towards the equator because the warm air here has low pressure. It's less dense, so it creates kind of a vacuum that will suck in this cold air, and it cycles through over and over again. Okay, this whole process is driven by the convection and uneven heating of Earth's surface. Okay. I just talked about this, but the reason that this air gets sucked in back towards the equator here is because of an area of low pressure created by less dense air that creates kind of a vacuum that sucks the air in. That's not super duper important, but I just thought you might want to know why it gets sucked in this direction. Okay. So it's important for you to realize that Hadley cells aren't happening in just one spot above the Earth. It's kind of like a tube of air current that wraps all the way around the Earth from 0 to 30, north and south. Okay, you can see here, hot air rises at the equator, deposits its precipitation and cools off, gets pushed northward and sinks, and then moves back alongside the equator. Okay, back alongside the Earth towards the equator. Same thing happening in the south. Okay. Now, Hadley cells are really important because they're responsible for biome distribution. Okay. Like I said at the beginning, rainforests are located at the equator because all that warm, moist air is at the equator, driven by the sunlight and evaporation. And the precipitation is all happening at the equator, which is why we see rainforests there. Deserts we tend to see around 30 degrees north and 30 degrees south because of that cool, dry air that is descending. Okay, that dry air that deserts are known for, low precipitation. And you can see that if you look at the map. Rainforests are located primarily at the equator, and for the most part, deserts are located about 30 degrees north or 30 degrees south. Okay, it's not a hard and fast rule, but it does help explain some biome distribution that we see. It's kind of neat. And it's even more evident if you take a look at this map. You can see a very stark line between the desert and the forest. So we talked about the convection and uneven heating of Earth's surface, but the Coriolis effect does come into play because as this wind travels from 30 degrees north towards the equator along Earth's surface, it's going to get deflected by the Coriolis effect. Okay? And you can see that if you look at this diagram. As wind travels from 30 north towards the equator, it gets deflected to its right. As wind travels from 30 south to the equator, it gets deflected to its left. This, as you can see, is going to push air and water in this western direction across the Pacific Ocean. That's going to come in handy when we learn about El Nino in a couple days. And you can see the effect of the Coriolis on all these winds in relation to the Hadley cell, from 30 south to the equator, getting deflected to the left, All of these are all from the Hadley cell. All from 30 degrees north to the equator, getting deflected to their right. That's all from the Hadley cells. Okay. And now I want to talk about ocean currents. These are oftentimes driven by wind, so they go hand in hand. One of the most famous ocean currents is the Gulf Stream, which travels up the east coast of the United States, carrying warm water and air from the Pacific, shooting it over towards Europe, okay, making Europe a little bit warmer than it should be otherwise. This Gulf Stream was discovered by none other than Benny Franks in 1768. The U.S. Post Office was wondering, why does it take us so much longer to sail from Britain to U.S. than it does to sail from the U.S. to Britain? It's the Gulf Stream. They didn't know it at the time, but Ben Franklin asked a bunch of merchant ships to take data, temperature of the water and their coordinates, so that way he could map changes in temperature in the ocean, and that's how he discovered the Gulf Stream. So that's pretty neat that he figured that out, 300-something years ago. I don't think I could do that today. So my hat goes off to you, Ben Franklin. And the ocean currents can be put into these categories of ocean gyres. These are patterns that we see of ocean currents. There are 5 main ocean gyres in the different oceans, and you might notice in the north the gyres spin clockwise, and in the south they spin counterclockwise. This again is due to the Coriolis effect. We also see patterns in heat, where the water traveling near and away from the equator is warm because it gets hit by that the direct solar radiation from the sun, and water traveling away to the equator or far from the equator is not getting hit by direct sunlight, so it's much colder. Okay, so we tend to see patterns in heat as well. Ocean gyres form for a couple of reasons. One, surface currents and the Coriolis effect, like I just talked about, will drive some ocean gyres, but deep water currents are driven by salt and temperature, and that's all about convection, right? We talked about how warm things rise and cool things sink. That's true for water as well. And salt also plays a role. Salt water is denser than fresh water. If you combine these two ideas of salt and temperature controlling ocean currents, we can refer to that as thermohaline circulation. Thermo meaning temperature or heat, and haline meaning salt. Think of halogens on the periodic table like chlorine that form salts. The thermohaline circulation can be exhibited by the ocean conveyor belt, which is a very large global ocean current driven by cold, salty water that is very dense and warm, fresher water that is less dense. Okay, I'm not saying that it's fresh water, but relative salinity is less, so it is less dense. And these currents can pick up stuff as they travel, right? Anything that gets caught in the current is going to get trapped in this gyre. And we see that in this Pacific gyre here with the Great Pacific Garbage Patch. You may have heard of this before. It weighs over 7 million tons, but it's not really a patch. It's more like a soup with lots of microplastics. It's very large, it's very deep, and believe it or not, it's almost 50% discarded fishing nets. So while it's good that we don't use plastic straws as much, that's not the primary contributor to plastic pollution. Plastic pollution isn't the only human impact on ocean currents. Climate change is having a big impact. As climate change continues, it's going to melt glaciers, and that is going to change the ocean circulation, right? Glaciers have cold water, which could mess with the temperature of the ocean currents, and they're also made of fresh water, which could mess with the salinity of the ocean currents. So we need to think about how we can reduce our carbon output. A great example of this that you must be familiar with is the Gulf Stream. The Gulf Stream carries warm water to Europe, explaining why the United Kingdom is so much warmer than its counterparts across the ocean at the same latitude in Canada. Canada's freezing cold, and the UK is not so bad. The reason for that is the heat brought over by the Gulf Stream. But as climate change continues and ice in Greenland starts to melt, that's going to inject fresh water into the ocean and reduce the salinity, and it's going to inject very cold water into the ocean and reduce the temperature. As we discussed, the temperature and the salinity are what drives these currents. So this could very well disrupt the Gulf Stream and actually result in Europe losing out on the benefits the Gulf Stream provides, and so Europe might actually get colder rather than warmer. That's all I got for you today. Thank you so much for tuning in, and I will see you next time.